The Earth has changed so many times and undergone significant transformations since its formation. How life emerged from non-life remains a significant scientific mystery. However, we do have a current best guess for the beginning of life on Earth, which we estimate to be around 3.8 billion years ago. But before we delve into that, let's start from the beginning and take a trip back in time. The Earth did not always exist, and it was not always hospitable for life. Approximately 4.6 billion years ago, our solar system was just a cloud of dust and gas known as a solar nebula. Around 4.5 billion years ago, the solar system settled into its current layout. The Earth's rocky core formed first, with heavy elements colliding and binding together. Dense material sank to the protoplanet's center, and lighter material built up the crust. During its formation, the Earth experienced a significant impact that propelled pieces of the young planet into space and formed the Moon, which took up orbit around the young planet. This was known as the Paleoarchean era, when the Moon was still very close to Earth and likely caused tides of more than 300 meters high. Hurricane-force winds blasted through the planet, and the evolutionary process began. During this time, the new Earth was a hostile place. The flow of the mantle beneath the crust caused the movement of large plates of rock on the planet's surface. Collisions of these plates created huge mountains and volcanoes that continually erupted, spewing out enormous amounts of lava and gases, and the reefs were created in the oceans. At this time, the protoplanet barely had an atmosphere. But as the planet cooled, gravity captured those gases from the volcanoes. Water was deposited on Earth by the collisions of many comets and asteroids. Another critical factor for life to emerge on our planet, aside from water, is its distance from its star, the Sun. Earth sits in what's called the Goldilocks zone, which puts it close enough to the Sun to allow liquid water to exist on the Earth's surface. Before life even began or had a chance on Earth, radiation from our star was the primary source of energy on our planet, just as it is today. The early Earth had very little oxygen, if any at all, and it's theorized that solar energy provided the jumpstart that transformed simple organic molecules into more complex ones, which became the building blocks of biology and life. Life likely developed in undersea alkaline vents and was probably based on ribonucleic acid, a nucleic acid that is present in all living cells, rather than deoxyribonucleic acid, an organic chemical containing genetic information and instructions for protein synthesis. At some point during this time, a common ancestor gave rise to two main groups of life, bacteria and archaea, although exactly how this happened is still uncertain. For billions of years, tiny microbes and single-celled organisms evolved and began feeding on methane around 3.6 billion years ago, and at the 3 billion year mark, evidence of viruses was found, although some argue that viruses could be as old as life itself. Sometime during Earth's early history, the planet took a turn towards habitability when a group of microbes known as cyanobacteria evolved with the ability to turn light and water into energy and release oxygen in the process. Dissolved oxygen caused iron in the oceans to rust and sink to the seafloor, which formed striking red-banded iron formations. But between 2.4 and 2.1 billion years ago, something incredibly remarkable and disastrous took place in this early cycle of life. The poisonous waste produced by these evolved photosynthetic cyanobacteria, oxygen, built up in the atmosphere, causing anaerobic bacteria to die off, leading to the Earth's first mass extinction, which some call the Great Oxidation Event. How can oxygen be toxic, you might be asking? Oxygen became toxic because of high levels, overwhelming the natural antioxidant defense system of any living microbe or bacteria at the time. Basically, these cyanobacteria in the form of algae ate themselves to death, causing a global extinction. But the worst was yet to come. Around 2.3 billion years ago, the Earth froze over, possibly as a result of the Great Oxidation Event, and volcanic activity on the planet slowed down. Over time, the ice melted, indirectly releasing more oxygen into the atmosphere. This gave way to the Neoproterozoic era, where protozoans such as Paramecium, amoebas, and Melanocerillium evolved. The first animal cells were different from plants, and these cells began feeding on plants, becoming the first herbivores. However, during this era, the Earth froze again at least 2 more times, which stunted evolutionary development. Life finds a way, though, and during this time, fungi, worms, and other small, bilaterally symmetrical animals survived and evolved. Fast forward to the Paleozoic era. Complex life forms began to develop, including fish, arthropods, mollusks, and echinoderms. Plants started to show up on the surface of the Earth, and air-breathing animals started to walk, crawl, and slither on land. Meanwhile, sharks, horseshoe crabs, and starfish began to fill the oceans. At the beginning of the Devonian period, insects started to take form, and ferns were the common land plant. A prehistoric jawless fish with bony armor called cephalaspis, and crabs, large sharks, hagfish, and ratfish evolved. This gave way to the Carboniferous period, where the climate on Earth was thought to be tropical, with little change during the seasons, and gave rise to a new wave of strange creatures. Plants covered the Earth during this time, and the organic deposits of plant debris formed the world's first coal deposits, which humans are still burning today. The growth of these forests increased oxygen levels in the atmosphere, which peaked at around 35% compared to the 21% it is today. This alone might explain the size of the giant creepy crawlies that emerged. Some animals and insects may have developed in water and grew bigger as a way to protect themselves against the high levels of oxygen at the time. One of those was giant insects called Meganeuropsis, which closely resembled modern-day dragonflies, had wingspans of 63 to 68 centimeters, and could be seen in the skies during this period. An incredibly detailed fossil of a huge dragonfly that died 320 million years ago was discovered to have a wingspan of 0.75 meters. Deadly, gigantic centipedes, 2 meters long, crawled around with mammoth cockroaches and scorpions as big as 1 meter long. Amphibians began to diversify, and reptiles evolved into forms much like modern-day lizards with a backbone, allowing them to live and move on land. These amphibians were also huge, and some species were predatory, resembling modern-day crocodiles, armed with sharp teeth and reaching lengths of almost 6 meters long. And like modern-day crocodiles and alligators, some evolved to have a thicker, scaly skin, which solved the problem of their bodies drying out if they were out of the water too long. And for the first time, amphibians evolved to lay amniotic or air-breathing eggs on land, and that changed everything, since these animals could now live out of and away from water sources. The Carboniferous period gave way to the Permian period that began approximately 300 million years ago, just 50 million years before the dinosaurs. All the continents during this period existed as one large landmass called Pangaea. The first large plant-eating and meat-eating animals evolved during this time. Some of these creatures could be mistaken for dinosaurs, but they were actually more closely related to mammals and reptiles. One of these bizarre creatures was Diplocaulus. It looked a little like a salamander that averaged around 1 meter long, but its head was shaped like a boomerang. Another new reptile on the planet was the iconic Dimetrodon, which grew to about 5 meters long and had a large sail on its back, which is likely used to regulate its body temperature. In the oceans, fish with true bony skeletons evolved. Sharks and rays flourished, as well as sponges and corals. On land, insects evolved with adapted mouthparts that allowed them to pierce and suck. But around 252 million years ago, the Permian period came to an abrupt end by a cataclysmic event that caused mass extinction. In 2001, scientists made a chilling discovery. A massive comet or asteroid, similar to the one that put an end to the dinosaurs, wiped out the synapsids and other creatures 200 million years earlier. But how did scientists come to this conclusion? Molecules of helium and argon gas were found locked in carbon in high proportions that could have only come from space. It's estimated that the asteroid or comet was between 6 and 12 kilometers wide in diameter. Researchers say the strike would have released energy 1 million times greater than the biggest earthquake of the last century. Aside from this discovery, there's some evidence that current-day Siberia and China experienced volcanic eruptions on an unimaginably massive scale, and those eruptions created dust and ash clouds that blocked out sunlight. Not only that, but over 1 million years, 3 million cubic kilometers of lava poured out of the ground, covering the entire planet in a layer 10 meters thick. The asteroid impact, combined with volcanic activity, was the proverbial blast from a double-barreled shotgun. The Earth was once again a very unhappy place. The combination of these two events resulted in what's called the Great Dying. 90% of all marine animals and 70% of all land animals that were alive during this time perished. Scientists used to consider Mars a geologically dead planet. It's smaller than Earth and loses internal heat faster. In the past, there was a lot of activity in its depths, and there are many traces of huge volcano eruptions on its surface. The largest volcano in the solar system, Olympus, can be seen from Earth even with an amateur telescope. But volcano eruptions on Mars stopped a long time ago. The planet's interior cooled and solidified, and the internal cooling weakened its magnetic field. The solar wind blew away the atmosphere, and the remaining water froze. But recently, Mars has become more active. Everything changed when astronomers studied thousands of images of the Martian equatorial region. The images were taken between 2006 and 2020 by the NASA Mars Reconnaissance Orbiter. The HiRISE camera took the images at an altitude of 300 kilometers above the Martian surface. The images allow us to distinguish individual objects with a size of up to 1 meter. The study revealed a large number of landslides and debris flows on the slopes of the Martian volcanoes. Scientists have discovered more than 4,500 traces of rocks that have left characteristic patterns in the shape of a Christmas tree, which usually happens after a strong earthquake. The longest trace is more than 2.4 kilometers long, and in total, these traces are around 900 kilometers long. About a third of the traces weren't present in images before 2006, indicating that they formed later. It is evident that only powerful underground tremors can move huge boulders. However, until recently, such tremors were not found on Mars. What helped scientists discover that Mars became active? How did the recent samples taken from one crater almost come to life? And why will one of the most harmful gases on Earth be so crucial for Martian colonists? Since 2018, the InSight spacecraft has been using the seismic experiment for interior structure to monitor earthquakes. It recorded more than 1,300 tremors, but this is negligible compared to Earth where we record from 500,000 to 1 million earthquakes annually. Additionally, almost all the vibrations on Mars are very weak, up to 3 points. The strongest earthquake, with a magnitude of 4.2, was recorded in August 2021. In May 2022, the Red Planet experienced a magnitude 5 Marsquake, which on Earth could knock out windows in houses and slightly damage our infrastructure. But it was a significant event for Mars. Earthquakes on Earth are stronger due to the displacement of tectonic plates and volcanic eruptions, which is not that active on Mars. But the 5-point tremors indicate that tectonic processes are still ongoing in its depths. The movements and magma bursts are still happening. When magma rises, it causes the bending of a single lithospheric plate of Mars, which results in Marsquakes. However, does the geological activity on Mars bring us closer to solving the mystery of its habitability? We know Mars as a harsh and inhospitable world, extremely cold, with terrible radiation and no liquid water. And, of course, there are no elephants, tigers, or even mice on its surface, as they wouldn't survive such conditions, and we could easily detect them with telescopes or rovers. But we wouldn't be able to detect microorganisms with these tools. Microorganisms are capable of surviving in extreme conditions on Earth, so there is a possibility that they could also exist on Mars, especially in its depths, where it's warmer and there's no fatal radiation. Additionally, the discovery of subsurface lakes on Mars is an exciting finding as it suggests the possibility of liquid water, which is an important ingredient for life as we know it. In 2018, radar instruments on the Mars Express spacecraft orbiting Mars detected a large underground lake on the planet's southern pole, as well as 3 smaller bodies of water nearby. The lakes span an area of over 75,000 square kilometers. This region is located in the Planum Austral, a large ice-covered plain. In 2022, instruments on the ExoMars orbiter showed that there are also giant reserves of frozen or liquid water in the Valles Marineris canyons. They are hidden inside a canyon system running along the equator of the planet. The water in the canyons covers an area the size of the Netherlands. It is located very close to the surface of the planet, within the top 3 feet of soil. On Earth, similar subglacial lakes in Antarctica have been found to contain microbes, fish, and other organisms. This could also be the case on Mars. A small amount of heat is retained beneath the surface of Mars from the planet's interior, but it may not be enough to melt the ice. This means that lakes may be frozen due to a high concentration of salt. If it's 20 or more times salter than Earth's oceans, even microorganisms would not survive. In order to understand this, scientists are trying to determine the composition of water in the underground lakes. They are also searching for signs of life in dried-up surface water bodies. Once, many lakes and rivers flowed on Mars when the planet was warmer and had an atmosphere. Many different organisms could have lived in such bodies of water, but up until recently, we couldn't find any traces. In September 2022, the Perseverance rover made a shocking discovery. It found organic molecules near ancient water sources. This wasn't the first time that rovers have found organic matter on the red planet, but this discovery is important because it was made in a place of an ancient river-lake merger, particularly favorable for life. It is located in the Jezero crater, 45 kilometers in diameter. The delta formed about 3.5 billion years ago and had been accumulating sand, dirt, and salts over time. Perseverance has extracted the largest amount of Martian organic molecules from this mixture to date. On Earth, fossils of ancient organisms are also commonly found in such sedimentary rocks. The Sherlock instrument on the Mars rover Perseverance, which is designed to identify organic and chemical substances, scanned molecules from the Jezero crater. Among other elements, it detected hydrogen atoms linked to carbon atoms. Carbon is crucial for life and may indicate biological activity. It's also important to note that the organic molecules in the Jezero crater sediment are intertwined with sulfates. On Earth, sulfate deposits preserve organic matter and often contain signs of life. However, the molecules in the crater may have formed through natural processes. Scientists will be able to determine their origin more accurately once samples are brought back to Earth, which NASA plans to do in future missions. Meanwhile, scientists have discovered other hints pointing to the possibility of life on Mars. Recently, the Curiosity rover detected an unusually high level of methane on the planet, 21 parts per billion units of volume. So, what does this tell us? Methane in higher concentrations is found in the Earth's atmosphere and is formed due to the emissions of living organisms. Scientists are planning to find out if the gas on Mars is also related to the activity of its inhabitants. If the methane had formed a long time ago, it would have already broken down into its component elements. Another possibility may be that the gas is a product of interaction between rock and water. But methane isn't the only gas scientists are curious about. Carbon dioxide, considered harmful on Earth, may soon become invaluable on the red planet. The experimental device MOXIE, the size of a toaster, was brought to Mars on board Perseverance. Its parts were printed on a 3D printer from a nickel-based heat-resistant alloy. Its composition also includes a lightweight aerogel for heat retention and a thin external gold coating that reflects infrared radiation. Thanks to this, the unique device is able to withstand a temperature of 800 degrees Celsius at which gas transformation occurs. MOXIE has recently produced pure oxygen from CO2. It works by separating oxygen atoms from the CO2 molecules. The byproduct, carbon monoxide, is released into the atmosphere. The tool is designed to produce up to 10 grams of oxygen per hour. However, after an hour of operation during the first test, the gas output was about 5.4 grams, enough to let an astronaut breathe for about 10 minutes. The device is particularly valuable because it is virtually unlimited in terms of raw materials, as the atmosphere of the red planet is 96% carbon dioxide. Also, MOXIE uses regolith, which covers the entire surface of Mars. After processing, this soil becomes fuel, air to breathe, or, combined with hydrogen, water. NASA and SpaceX CEO, Elon Musk, closely follow scientists' discoveries on Mars. The head of SpaceX is actively preparing for flights and promises that we'll see the first images of astronauts on Mars in 2029. 14 Raptor engines of the Starship spacecraft have already been tested. Meanwhile, NASA has also chosen Starship as the first crewed landing module for the Moon. If everything goes according to plan, astronauts will land on the lunar surface in 2024 as part of the Artemis 3 mission. Then, by 2040, NASA plans to send a manned spacecraft to Mars, and the Moon will become a base for refueling. But after the flight, the colonists will still have to settle in extremely difficult conditions on Mars, and that's where new discoveries by scientists will come in handy. Most likely, as experts say, the first crew will land near the planet's equator. The canyon with liquid water in the Valles Marineris will be the perfect landing spot. Water is necessary for drinking, growing crops, and sustaining household needs. The settlers will also need oxygen, as the air on Mars is composed of a toxic mixture of carbon dioxide, nitrogen, and argon, and MOXIE is getting closer and closer to solving this problem. In addition, Elon Musk plans to refuel rockets directly on Mars for the return trip to Earth. To do this, he wants to build a factory on the red planet to produce methane and liquid oxygen from water ice and atmospheric carbon dioxide. If researchers do find microorganisms in the subglacial lakes, it will also be a step forward in colonizing the planet. Local microorganisms will be perfectly adapted to the harsh conditions of Mars by studying them. It will be easier to find ways to protect against the variety of climatic dangers of the red planet. That's all for today. Thanks for watching. Share your opinions in the comments and don't forget to like and subscribe to new videos. See you soon.